Hey everyone, welcome back to another episode of Java Internals Crashcasts. I'm Sheila, and with me today is Victor.
Hi Sheila, and hello listeners. Today we are wrapping up our Advanced Topics season with a summary episode. It's been quite a journey through some really deep and fascinating topics.
Absolutely, Victor. This season has covered everything from the fork-join framework, concurrent design patterns, performance and scalability, Java memory model, all the way to garbage collection, JVM internals, reactive programming, and concurrency enhancements in Java 9 and beyond. That's a lot of ground.
Indeed it is. But before we dive into summarizing everything, let's make sure our listeners are ready and have some context on what we'll be summarizing today.
Great idea. For our listeners, we'll touch upon key concepts, highlight important edge cases, and discuss real-world implementations. Here are the main sections of today's episode. 1. Fork-join framework. 2. Concurrent design patterns. 3. Performance and scalability. 4. Java memory model. 5. Garbage collection. 6. JVM internals. 7. Reactive programming. 8. Concurrency in Java 9+. But first, let's start with a quiz question to get your brains ticking. Ready?
Oh, I love quiz questions. Go ahead, Sheila.
All right, here it is. In the fork/join framework, what's the primary advantage of using a recursive task over a recursive action? And can you think of a practical example where recursive task would be more beneficial?
Great question. Let's break this down. The fork-join framework is designed to help us take advantage of multi-core processors by breaking down tasks into smaller subtasks that can be executed in parallel. Recursive task and recursive action are both abstract classes used for this purpose. But there's a key difference. Recursive task returns a result upon completion, while recursive action does not. Now, without giving away the answer, think about scenarios where you need a computed result from your parallel tasks versus scenarios where you just need the tasks to execute without needing their outcomes. It's a subtle yet important difference. Stay tuned for the answer towards the end of the episode.
Very intriguing. I can't wait to reveal the answer later. Now let's start our summary of the key topics we covered this season. Victor, can you get us started with the fork-join framework?
Sure thing, Sheila. The fork-join framework was introduced in Java 7 to provide a powerful tool for parallel processing. Think of it like a team working on a big project. The framework breaks down a large task into smaller tasks, much like dividing a project into smaller assignments. These smaller tasks are then executed in parallel using a pool of worker threads, similar to team members working on different parts simultaneously. When all parts are done, the results are combined. This approach is particularly useful for tasks that can be broken down into smaller, similar subtasks.
That's a great explanation. Moving on to concurrent design patterns, we discussed several important ones. Can you highlight a few, Victor?
Absolutely. Concurrent design patterns are like recipes for solving common problems in multi-threaded programming. For instance, the producer-consumer pattern is like a bakery operation. Bakers, producers, make bread and put it on shelves, while customers, consumers, take bread from the shelves. This pattern helps manage scenarios where data is being created and processed at different rates. Another pattern, the read-write-lock, is like a library system where many people can read a book simultaneously, but only one person can update or write in the book at a time. These patterns help us build more efficient and reliable multi-threaded applications.
Great analogies. Let's talk about performance and scalability next. We touched on Amdahl's law, contention, coherence, and benchmarking. Why are these important?
Performance and scalability are all about making our applications run faster and handle more work as they grow. Amdahl's law helps us understand how much faster our program can run when we add more processors. It's like understanding how much quicker a team can complete a project by adding more people. Contention is when multiple threads compete for the same resources, like multiple people trying to use the same tool at once. Coherence ensures that all parts of the system see the same data, like making sure everyone in a team meeting has the same information. Benchmarking is how we measure performance, like timing how long it takes to complete different tasks. Understanding these concepts helps us build faster, more efficient applications.
And then we delved into the Java memory model, which is all about how threads interact through memory. Can you explain that, Victor?
Sure. The Java memory model is like a set of rules for how different parts of a program share information. Imagine a group of people working together, but each person has their own notepad. The memory model defines how and when the information on these notepads gets shared with others. Key concepts include the happens before relationship, which ensures that actions in one thread are visible to another thread in a predictable order, and the volatile keyword, which is like a special note that everyone can see immediately when it's changed. Understanding these rules is crucial for writing programs that work correctly when many things are happening at once.
Good points. Now let's move on to garbage collection. Why is it such a critical topic?
Garbage collection is like having a helpful robot that cleans up the mess in your program's memory. It automatically manages memory, which is crucial for keeping our applications stable and performing well. We discussed various types of garbage collection algorithms, each with its own way of cleaning up. It's important to understand how this cleanup process works because it can affect how smoothly our programs run. Proper garbage collection helps prevent memory leaks, which are like forgotten boxes taking up space in a storage room, and optimizes overall performance.
Exactly. JVM internals was another deep dive we took this season. We explored class loading, JIT compilation, and the hotspot VM. Can you give a brief summary?
Sure. JVM internals are like peeking under the hood of a car to see how it runs. Class loading is similar to gathering all the tools and parts you need before starting work. Just-in-time, JIT, compilation is like a skilled mechanic who learns to do tasks faster over time. The hotspot VM is the engine that powers Java applications, designed to run them efficiently. Understanding these internals helps us write better code and troubleshoot problems more effectively, just like knowing how a car works helps you drive it better and fix issues when they arise.
And we didn't stop there. Reactive programming was a big highlight too. What's the takeaway from that, Victor?
Reactive programming is about building systems that respond quickly to events, kind of like a well-organized emergency response team. The Flow API in Java 9 and beyond helps manage streams of data, similar to how a traffic control system manages the flow of cars. We also looked at libraries like ArcsJava and Project Reactor, which provide tools for handling large amounts of data efficiently. These approaches are great for building applications that need to handle lots of information or users at once, keeping everything responsive and smooth.
Thank you, Victor. We also touched on concurrency enhancements in Java 9 and beyond, such as var handle, improvements to completable future, and the stack walking API. How do these enhancements benefit us?
These enhancements are like upgraded tools in our programming toolbox. var handles offer new ways to work with variables in multi-threaded environments, similar to having precision tools for delicate work. Completable future improvements make it easier to write code that does many things at once, like a master chef managing multiple dishes simultaneously. The stack walking API gives us a more efficient way to look at what our program is doing, like having a smart assistant that can quickly tell you the history of actions. Together, these features make it easier and more efficient to write programs that can do many things at once.
Perfect. Before we wrap up, let's reveal the answer to our quiz question. So, in the fork-join framework, why would you use a recursive task over a recursive action?
Great question. You'd use a recursive task when you need the task to return a result. Imagine you're calculating the sum of a large set of numbers. Each recursive task could sum up a portion of the numbers and return its result. These results are then combined to get the total sum. On the other hand, recursive action is used when you just need tasks to execute without returning results, like updating records in a database. The key is to choose based on whether you need a computed result from your parallel tasks.
Thanks for that explanation, Victor. And that's a wrap for the Advanced Topics season. To summarize, we've explored the fork-join framework, various concurrent design patterns, important aspects of performance and scalability, the Java memory model, garbage collection, JVM internals, reactive programming, and concurrency enhancements in Java 9 and beyond. Next in our series, we'll dive into Java version comparisons, which will help you understand the differences and improvements between various Java versions.
That's right, Sheila. It's going to be very insightful to see how Java has evolved. Remember to subscribe to our podcast and rate us if you find these episodes helpful. Your feedback means a lot to us.
Thanks for joining us today, and stay tuned for our next episode. We hope you've enjoyed this journey through advanced Java topics as much as we have. Until next time, happy coding!